Welcome all my dear students to Sudharma's physics classroom. Today we are going to start with a new chapter, magnetic effect of electric current. In the previous chapter we have already understood the lighting effect of electric current and heating effect of electric current, and we are going to study in detail about magnetic effect of electric current in the coming chapter. So in today's video I will be discussing the basic terms related with magnetism. What are the properties of a magnet? What is magnetic field? What is magnetic field line, etc. Okay, so let's start with the topic. So when somebody asks you what is a magnet, immediately some 2-3 terms comes to your mind, right? What are those 2-3 terms? Basically we know that the magnet has two poles, right? So it has a north pole and a south pole, right? It has two poles, north and south pole. Now, what else comes to your mind? Immediately when a magnetism concept comes to your mind, you know, the compass needle also comes to our mind, right? Compass needle. What is compass needle? What is it made of? How many of you know what is this compass needle is made of? We know that it points in some direction, right? It points towards the north. We can use it to identify the direction, right? So, this compass needle is made of a magnet itself. It is a magnet itself, but it's a very thin magnetic needle. So, if a compass needle is kept at one place, if there is no other magnet, compass needle will be aligning in the north-south direction, right? Now, as we said, magnet has two poles. Here you can see the north pole of the bar magnet is coming towards the north of the magnetic needle, right? So, north, red color is indicating north in this, right? So the north of the needle is just getting repelled from the north pole of the bar magnet. At the same time, the south pole of the needle is getting attracted towards the north pole of the bar magnet. So this is one of the most important properties of a magnet. Similar poles will repel each other, or like poles will repel each other, unlike poles will attract each other. Similar poles means what? If you have a north pole and north pole approaching, they will be repelling from each other. They just go away from each other. Similarly, if a south and south pole approaches, they will also repel from each other. This is what is meant by like poles will repel each other. If a north and south pole comes towards each other, then they will be attracting. Okay, they get attracted towards each other. That is what you can see in this video. Okay, now another type of magnet, bar magnet and horseshoe magnet. Horseshoe magnet is our U-shaped magnet. These are the common magnets we use in our school laboratories. Okay, so horseshoe magnet means it is a U-shaped magnet like a horseshoe, and that also has north and south poles. See, these are the basic things you know from elementary classes. Now let's come to the terms related with a magnet. The first one is magnetic field. What is magnetic field? The space around a magnet where magnetic force is exerted is called magnetic field. The space surrounding a magnet where magnetic force is exerted is called magnetic field. So this is the definition of magnetic field. Let's analyze what is the meaning of this statement. So when you keep a bar magnet or any type of magnet, if you have an iron needle, iron is a magnetic material. Say this is the iron needle. So what happens? Magnetic material will be attracted towards the magnet, right? Any part of the magnet will attract this magnetic material. So the iron needle gets attracted towards the magnet. Now I'm going to take it away from the magnet. Say I'm keeping the needle here. So we can experience a force, but that force will be a little bit less compared to this position, right? If I'm taking that magnetic material somewhere away, very much away from the bar magnet, then that magnetic material will not feel that force of attraction, right? So nearby the magnet, we can experience that force. Little bit beyond that magnet also we can experience the magnetic material can experience the attractive force, but beyond a certain region magnetic materials will not experience a force because of this particular magnet. That means that the magnetic material is outside the magnetic field. Okay, so somewhere around the magnet, whenever you keep a magnetic material, there will be magnetic force of attraction. If you go beyond that region, then there is no force of attraction, right? So up to whatever region we are able to get that magnetic force, then we can say that that is the magnetic field. And now coming to this diagram, we have a bar magnet and you can see a beautiful pattern there. You know what is that? It's iron filings. Okay, iron filings are spread. We have not made into this shape. We just sprinkle iron filings. What is iron filings? Powdered iron. Okay, powdered iron. Say iron in very small grains. Okay, that's powdered iron. Okay, so if you sprinkle this iron filings simply on the sheet of paper where you kept the magnet, you will be seeing that the iron filings will be arranging in this beautiful pattern. See, nearby this magnet you can see they are very much crowded, right? Very close to each other. But when you move away from the magnet, they will be moving away. I mean the distance between the field lines will be more. And it automatically aligns in this pattern. So we can understand that it is aligning in the shape of the magnetic field of a bar magnet. See, nowadays different shaped magnets are available, especially with toys, right? In your house itself, you can see, you may see some different types of magnets. Some ring type magnets will be there. Spherical magnets are there. Then oval shaped magnets are there. Bar magnet and horseshoe magnet, that is what we use in our school laboratories for experimental purpose. Okay. So at the end of this chapter, we will be learning how to make these different shaped magnets also. Okay. So each shaped magnet will have different types of magnetic field. The shape of the magnetic field will be different for different type shaped magnets. So this magnetic field shown here, that is of a bar magnet. Okay. So now let's understand how to plot the magnetic field of a bar magnet. So to plot any magnetic field, we have two methods. One is spreading the iron filings and observe what is the pattern. So the problem with that is we won't know in which direction the magnetic field is. Okay. So magnetic field is a vector quantity. So we have to know the direction also. Strength we can understand by observing the concentration of the field lines. But in which direction the magnetic field lines are, or in which direction the magnetic field is there at that particular point, we can understand that using an experiment. This is a simple experiment. Those who have a bar magnet or any type magnet and a compass needle at home, we can try it very easily at home. This is not at all difficult experiment. This is a very easy experiment. What you need is a magnet and a compass needle and a pencil. Okay. So first you keep the bar magnet on a sheet of paper. Then you keep a compass needle nearby the north pole of the magnet. Okay. So you keep a compass needle near the north pole of a magnet. So the north pole of the needle will be deflecting away from the north pole of the bar magnet, because north and north will repel from each other. Okay. So what you do is you just mark the position of the direction of the compass needle with a dot. Then you bring that compass needle on that dot. Then again follow the path of the needle. Follow the path of the compass needle. You will be seeing that you are just getting directed towards the south pole of the bar magnet. Okay. So first of all, you are going to keep the compass needle near the north pole of the magnet. So the magnetic needle will be pointing in one direction and you mark that position with a sharp pencil. Then keep that compass needle again on that mark. Then continue the process. You see that you're getting a pattern like this. So after you reach nearby the south pole, we can stop that procedure. Then you're going to just join these dots. Okay. So we were following the north pole of the compass needle and it is reaching towards the south pole of the bar magnet. Okay. So the direction of the magnetic field is from north to south. Hope you are understanding. So this is one magnetic field line I have plotted. Similarly, we can plot many magnetic field lines. That is what you can see in this diagram. So this is the same pattern we have seen with the help of iron filings also, right? Observe carefully. And the interesting thing is nearby the poles, you can see the magnetic field lines are very much crowded, right? They are very much crowded. That means the strength of the magnetic field is more nearby the poles. When you move away from the bar magnet, you see this, the distance between the magnetic field lines is increasing, right? So that shows that the magnetic field strength is decreasing when you move away from the bar magnet. And always you can see that the magnetic field lines are from north to south. Okay, the path traced by a north magnetic pole free to move under the influence of a magnetic field is called as magnetic field line. So why the statement is coming like that? See, it's a path traced by a north magnetic pole free to move under the influence of a magnetic field. So which was the north magnetic pole free to move? The compass needle's north pole we have chosen here, right? For the experiment, we have taken the north pole of the compass needle. We were following the path of the north pole of the compass needle. So that was moving under the influence of the magnetic field of this bar magnet. So we could plot the magnetic field of this bar magnet. Okay. So what we have observed here is the magnetic field lines will be from north to south outside the magnet. And very important property of magnetic field is magnetic field lines are closed curves. Let's see one by one what are the properties of magnetic field lines. These are the repeated questions of our exams. Explain the properties of magnetic field lines. So we have seen the magnetic field lines coming from the north and going towards south, right? So we can say that magnetic field lines emerge from north pole and merge at the south pole. It will be just coming out of, right? It's coming out of this north pole and reaching to the south pole. Okay. So this is the important property of magnetic field line. So magnetic field lines emerge from north pole and merges at the south pole. The strength of the magnetic field is indicated by the degree of closeness of the field lines. Strength of the field lines can be indicated, or we can understand by observing the magnetic field line. If they are very crowded, at that region the magnetic field strength will be more. If they are separated apart, if there is more distance between the magnetic field lines, then the strength is less. And no magnetic field lines intersect each other. Very, very important property. No magnetic field lines intersect each other. So in this experiment, when I'm doing the experiment, I'm going to plot another magnetic field line. So I'm doing the experiment, and by chance, suppose I'm getting a field line like this. Suppose they are meeting at this point. Okay. If they are meeting, this is completely wrong, because we were following the path of the north of the compass needle. If they are meeting at this point, that means that compass needle has to show two directions at that single point, because the direction of the magnetic field at a point is indicated by the direction in which the compass needle is pointing. Okay. So if two magnetic field lines are intersecting, that means that the compass needle has to show two directions simultaneously. Think, is it possible? You have a compass needle, and at the same time it cannot indicate two directions. At one time it indicates one direction, right? If you change the position in a magnetic field, it can show another direction. That means that is at another situation. But simultaneously at an instant it cannot show two directions, right? So if when you perform an experiment, if your field lines are coming like this, then this is going to be wrong. Maybe some change in the position of the magnet happened. So you can do one thing to avoid this problem. Once you keep the bar magnet on the sheet of paper, you just trace the outline of the bar magnet. Okay. So when you trace the outline of the bar magnet, see, we are not sticking this magnet to the sheet of paper, right? So when we do the experiment, there is more chance for this magnet to move here and there, because our hands may touch on that, and slight movement of the bar magnet itself cause mistakes in the experiment. So in order to avoid that, you will be drawing an outline of this bar magnet on the sheet of paper. If by chance if it moves, you can just bring it back to the same position. Okay. So that is the important property. Two magnetic field lines never intersect, or no two magnetic field lines intersect each other. Then magnetic field lines are closed loops. Closed loops. When we were plotting the magnetic field lines came like this, right? What we could see is only outside the magnet. Outside the magnet, it is from north to south, and inside the magnet, it is from south to north. So now you will be thinking, how do we plot this south to north magnetic field in a bar magnet? Of course, that is not possible, right? Because it's a solid material, and how do we plot the magnetic field within the bar magnet? But in the coming videos, I will be explaining different shaped magnets made of electric current. When electric current passes through the conductor, it behaves like a magnet. That is our chapter name, right? Magnetic effect of electric current. I have taken this topic today because we need to know all these terms. These are the terms which comes repeatedly in the chapter, throughout the chapter. Okay, so in those ideas, in those examples where electric current passes through a conductor, through different shaped conductors, different shaped magnetic field patterns will be produced. In that, we will be clearly able to see the magnetic field lines passing from south to north within the magnet. Okay, inside the magnet it will be from south to north, outside the magnet it will be from north to south. So these are the important properties of magnetic field lines you have to learn. Now, normally if I give you a bar magnet, say I'm just giving you a bar magnet, there is nothing marked on that. So I'm asking you to find out what is the north pole, where is the north pole of the magnet and where is the south pole of the magnet. How do you understand which is the north pole and which is the south pole of this magnet? So if nothing is given, no other device given, see if a compass needle is given, we can try. I am not giving you anything else. I am just giving you a bar magnet and asking you to find out the north and south pole. So what you can do is you can freely suspend it using a string. Just take a string, just suspend it. You can just hold it on your hand, then let it come to rest. It may just fluctuate sometime, and at last it comes to rest. Then you have to check in which direction it is aligned, and you know the direction in your place. So you can see that one of the sides will be aligning towards your north direction, north of your place, and one side will be pointing towards the south in your place, south direction. So the position, the side which is pointing towards north, that is the north pole of the magnet, and the side which is pointing towards your south direction, that is the south pole of the magnet. This is how we identify the pole of a bar magnet. So my question is, why a freely suspended bar magnet aligns in the north-south direction? I just told you we have to suspend it when it align, when one side will be pointing towards north, that is the north pole. But why? Why it is aligning? Why it can't align in the east-west direction? Here we have the answer with respect to the Earth's magnetism. Earth is a good magnet. It has a good magnetic field. So we can imagine a magnet in the form of a bar magnet. Of course, it is not in the form of a bar magnet, but we can understand that if the bar magnet is aligning towards north, that means there is a magnetic field where the south polarity is there, right? Because only the attraction takes place towards south, because north and south only will get attracted to each other, right? South and north gets attracted towards each other. So we can understand here the south pole, and we say that this north, the direction in which it is pointing is north direction in our place, right? But here the magnetic pole is shown as south. So the Earth's imaginary magnet south pole is at the geographical north. Okay, at the geographical north, we have the Earth magnet south pole, and at the geographical south, understand the difference, geographical south, at the geographical south, that means at the south pole, we have the magnet, Earth's magnet's north pole. It's just the opposite. Okay, at the north pole of the Earth, we have the south pole of the Earth's magnet. At the south pole of the Earth, we have the north pole of the Earth's magnet. That is why when we freely suspend a bar magnet, it aligns in the north-south direction. Hope you understood that. Now let me ask you a simple question. If you understood the properties of magnetic field lines, let's try to solve this question. So I have a magnet and the polarities are shown as X and Y. Now there is a clue for this question. This is the only clue given. Okay. Now from this diagram you have to identify the north and south of the bar magnet. Okay. you have to identify the north and south of the bar magnet, and you have to draw the direction of magnetic field at the positions B, C and D. I repeat the question. The bar magnet is given. The polarities are X and Y given here. So your job is to find out the north and south of this bar magnet. That is the first question. Which one, X or Y, which is north or south? Okay. So once you identify the north pole, definitely the other will be the south pole. At the position A, the direction of magnetic field is shown. So based on that, you can find out the north and south polarity. Okay. Now, the next question is, you are going to draw the magnetic field lines at the direction of magnetic field at the position B, C and D. You can draw, you just note down this diagram, draw this diagram in your book. Then draw the arrows inside these circles in whichever direction the magnetic field points at that position. So I repeat, magnetic field lines are from north to south outside the magnet. So if you have that idea in your mind, you will be able to solve this question. So let me see how many of you are going to solve this and put the answer in the comment box. If all of you solve this question, I will give you the answer for this question in the coming video. So before the coming video, I need all your answers in the comment box. Then if it is there, then definitely I will explain. See, most of you will be getting the correct answer. For those who didn't get the answer, I will be explaining the answer in the next video. Okay, so this is your homework for today. So I think it's time to wind up today's session. In the coming session, we will be discussing about Easted experiment, right hand thumb rule. So we are getting into the magnetic effect of electric current. All the basic things are done. We know what is magnetic field line, etc. Right? So we are into that. We are ready to learn this magnetic effect of electric current. So we will be learning Easted experiment. That is the first experiment which proved electricity can produce magnetism. So we're going to learn that in detail, and we're going to learn right hand thumb rule and the questions related to that concept. Okay. See, this magnetism chapter is a very, very interesting chapter. Okay. So if you are watching this video for the first time, please subscribe to the channel and click the bell icon for more updates. I will be coming very soon with Easted experiment. Okay. Thank you for watching. See you in the next class with Easted experiment. See you soon. Bye.